Good morning, everyone. This is Math 2008. Today is June 14th. We are going to work on 4.2 by the time we're done with the lecture. Hopefully, you will be able to do the problems assigned from 4.2. I know some of you have started already. Good for you. Um, if you can't do something, please send me a screenshot of your problem, a clear, high-res screenshot of your problem. One more thing, mention your course number. This is 2008. All right, guys. So I have my notes ready. I'm going to see what I can do. I think I'm having a little bit of technical difficulty. Maybe not. We'll get there. Don't worry. All right, here we are. So guys, we are starting 4.2. It's about prime and composite numbers. So let's write down those words. Prime and composite numbers. Okay. So how do we define these words? So last class, when we talked about divisibility, we learned that, 2 divides 4. Okay. Now, in this section, we'll be primarily concerned about natural numbers. And I'm going to list them here. 1, 2, 3, 4, 5, 6, dot, dot, dot. So which ones of these are prime numbers? Okay. So prime numbers have exactly two. Let's list a few more, guys. 7, 8, 9. Okay. Now your book defines prime numbers a little differently, guys. I'm going to define it like this. I'm going to tell you why. Okay, prime numbers are a number from this set, okay, that has exactly two divisors from this set. Um, for instance, 2 is a prime. 2 is divisible by 2, and 2 is divisible by 1. 3 is a prime. 3 is divisible by 3. 3 is divisible by 1. 4 is not a prime. 4 is divisible by 4, 1, and 2. 5 is a prime, is divisible by 5 and 1 only. 6 is not a prime. 7 is a prime because 7 is divisible by itself and 1. So if a number is only divisible by itself and 1, it is called prime number. Got it? All right. So that means 1 is not divisible, is not a prime because 1 is divisible by only one number, 1 for itself. So if a number is divisible by exactly two other numbers in this set, we call it a prime. Got it? Now, I'm going to write it down here. Prime number is divisible by exactly two distinct natural numbers. All right. What's a composite number? A composite number is divisible by more than 2, by at least, let's use the word at least, right? At least 3 distinct natural numbers. All right, so let's add a few more here. This is the set of natural numbers. That should be sufficient. Okay, these are the definitions we're going to stick to, prime and composite. By using these two definitions of prime and composite numbers, we can say one is not a prime. You want to remember that. Don't assume one is a prime. One is not a prime number. All right, so what's a composite number? Well, 4 is a composite number because 4 is divisible by 3 distinct natural numbers, 4, 1, and 2. 6 is a composite number. It's divisible by 1, 6, 2, and 3, which is at least 3 because it's 4. 4 is more than 3. So once again, these are the definitions we are going to stick to. A composite number is divisible by other prime numbers and 1. Okay, every composite number is divisible by at least one prime number and 1. The prime number is divisible by only itself in 1. Okay, has to be 2 distinct natural numbers. And 1 is not a prime number. 1 is, let's put it like this. 1 is, most of us know it's not composite. 1 is neither a prime nor a composite number. 1 is neither a prime nor a composite. All right, so we're going to stick to it. Don't tell me 1 is prime. And I don't want to hear, I read it somewhere in another book. This is how your book is treating the word prime, and we're going to stick to it. In the olden days, I've been told 1 was defined as a prime. Nowadays, we don't define 1 as a prime, so don't even go there. All right, guys. So prime factorization is going to be our next topic. So I'm going to pick a number, not too large. Clearly, 12 is not a prime number because 12 is divisible by 1, 12, and 3. So let's see what we can do. So how do we factorize 12 and what does it even mean? Well, let's do the thing and then we can discuss. So basically, factorization is something like this. 12 is equal to 3 times 4. Well, that's okay, but it's prime factorization, so all the factors have to be prime numbers. So there's a lot actually in this section, guys. So be a little patient today. We'll have a long class. So 4 is not a prime. Okay, no problem. But I can express 4 further in terms of prime factors, which is 2 squared. Now that I have everything in terms of prime numbers, this is called prime factorization of 12. If you don't care about the order, whether you're writing 2 times 2 times 2, 2 times 2 times 3, or 2 times 3 times 2, it's the same. So there is only one way of doing it. Um, we're going to write it like this in general. Okay, the custom is you start with the smaller one, the smallest one, and then you move up. And generally we don't write 2 times 2, we write 2 squared. Okay, and your book uses uh, mechanism. It's called factor 3. It's the same thing that I did here, but this is how they do it, and I'll do it that way. Okay, guys? I'm going to take another number. Let's say I'm going to take 75. Okay, I want to do the prime factorization of 75, and that means I want to express 75 in terms of prime numbers. All right, how do we do that? Well, let's break it apart and test if they are prime numbers or not. I'm going to break it apart like this. You break it the way you want to break it. Okay. Now, the way I see it, 75 is 25 And the good news is 25 is prime. Sorry, 3 is a prime number. So I'm good there. Okay. I can circle it because I don't have to do anything with it. Okay. Now, 25 is not a prime, but I can split it further into 5 by 5. And 5 is a prime. I'm going to write 5 here. I'm going to write 5 here. And I am going to circle it. Now, finally, I'll write it properly like I have done over there on the left. So I am going to say 75 is equal to 3 times 5 squared. This is called the tree method. It's very similar to the way I did here, but it's a little more visual. There's some problems like this in your, okay? In this context, I would like to mention one more thing. So it's called, you're going to hear it, it's called the fundamental theorem of arithmetic. Says each composite number can be written as a product of primes in one and only one way, except for the order of prime factors in the product. So basically, they're saying 75 has only one prime factorization. It's 3 times 5 times 5. Now, we don't care about the order. Okay, so if you write 5 times 3, it's not a different prime factorization. 12 has only one and one prime factorization. That's 2, 2, and 3. 2 times 2 times 3. That's all it means. All right, let's get rid of this. I'm not going to worry about this one is very basic, but I'm going to go over it. What does it say? If D is a divisor of N, let's take our example of 12. Okay, so 12, 3 is a divisor of 12. That's a fancy way of saying 3 divides 12. Okay, 3 divides 12, and the answer is 4, or the quotient is 4 if you want to be really fancy, right? If well, actually, guys, I'm going to go to a different slide, okay? I don't have to save space. Give me 1 second. It'll look a little better. All right, so I'm going to give you an example. I'm going to explain to you what this means. Intuitively, it makes a lot of sense. N is a divisor, D is a divisor of N. So suppose 12, and the divisor is 3, and the answer is 4. That means when 3 divides 12, you get an integer, you get a natural number as your answer, right? Now, they're saying 4 will also divide 12. Well, that makes perfect sense, right? If 12 divided by 3 is 4, then clearly 4 divided by 12 is 3. That's all they're trying to say. It seems very complicated, but it's not a complicated idea. Okay, very intuitive. That's all this theorem is trying to say, all right? I'm not going to worry too much about 4.14. All right, so guys, so far, we have learned about prime factorization and prime and composite numbers and factor tree. So how do we find prime numbers? Okay, so for instance, this is a page from a, what are they saying? What grade level? Grade one. It's a page from a grade one text. So we're going to do some grade one math. They are trying to show us, it's called sieve, I guess it's called sieve of Eratosthenes. Eratosthenes was a Greek philosopher and a mathematician and a scientist. There's a little Wikipedia snapshot about this mathematician. See, he was around um, during uh, 276 BC. He was Greek, which is modern Libya, was a part of Greece back then. Alexandria is in Egypt, but it was a part of Greece back then. But anyway, we're going to do some math that he taught us. Okay. So he taught us how to calculate with certainty the prime numbers in a group of numbers. So let's say I'm going to take this set of numbers. Okay. This is what he taught us. So bear with me. It's going to take a little bit of time, but it's worth doing it. And first graders are doing it. So might as well learn. You will be teaching it. That's what I mean. Okay. All right. So basically, I have listed all the numbers from 1 to 100. I would like to know how many of these are prime numbers. I'm going to use the technique taught by Eratosthenes, known as sieve of Eratosthenes. And um, how do we do it? Well, this is what he taught us. Okay. If you find the prime, find uh, the first prime, which we know one is not and two is, and circle it, circle it. And it's going to take a little bit of time, guys. Okay, so be a little patient. Circle it. Then cross out, ignore all the numbers that divide that are divisible by two. Basically, cross out all the even numbers, and it'll take a little bit of time. So I'm going to not cross out. I'm going to do something like this. What color? Red is good enough. It's going to get a little better, okay? But I'm going to do it patiently just to show you the steps because they're divisible by two. They cannot be a prime. I know that. I have to do one more thing. I don't want this thing to, not bad. Okay, so again, two is a prime, and these guys are not primes. Cannot be because they're divisible by two. Cross out all the multiples of two. Four is a multiple of two. 6 is a multiple of 2, 8 is a multiple of 2, 10 is a multiple of 2, so is 12, 14. So what I'm going to do now, I'm going to do a little cheating, if you would let me. Maybe it's not the good word, not a good word. So I'm going to hide this. I'm going to use it later. I'm going to take this and drag it down all the way. They are all gone. They cannot be primes. These are all gone. These are all gone. These are all gone. And these are all gone too. I got rid of all the even numbers. I got rid of 50 of them. That helps a lot. Now, 3 is a prime. I circle 3. 3 is a prime. I circle 3. I'm going to cross out all the third number, every third number. So 6 is crossed out. I'm going to cross out 9. Then 12 is crossed out. I'm going to cross out 15. Then 18 is crossed out. 21. I'm going to cross out 21. 24 is the next one, but that has been crossed out. I'm going to cross out 27, 21, 24 is crossed out. I'm going to cross out 27, 30 is crossed out. I'm going to cross out 33, 36 is crossed out. I'm going to cross out 39, and 42 would have been the next one, but I'm going to cross out 45, 48 is the next one, but that is crossed out. 51, and 51 is divisible by 3. Then 54 is crossed out. 57 is divisible by 3. I'm going to cross that out. You're crossing out every third number. 60 is crossed out. 63, 66, 69, 72 is crossed out. 75 is the next guy. And it's a fun activity for kids because they start seeing patterns, and you can probably already see the patterns here a little bit. 75, 78 is crossed out. 81 is the next one to go. So I don't have to test a lot, so it's not really that bad. 84 is crossed out. 87, let me double check. 87 is divisible by 3. 3 times 2, yes, it is. 90 is crossed out. 93 is the one that's divisible by 3. Remember, guys, 9 plus 3 is 12. 12 is divisible by 3, so is 93. I'm reviewing stuff from last class. 96 is crossed out, and the next one is 99. Okay, 5 is a prime. I circle it. And all the multiples of 5 are this column and this column. Okay, to, to keep things simple, I'm just going to extend this. These are all gone. Okay, 7 is a prime, and I have to be very diligent. Okay, every every seventh number will be removed. 1, 2, 3, 4, 5. 14 is already gone. 1, 2, 3, 4, 5, 6, 7. 21 is already gone. 1, 2, 3, 4, 5, 6. 28 is gone. 1, 2, 3, 4, 5, 6, 7. 35 is already gone. 1, 2, 3, 4, 5, 6, 7. 42 is already gone. 1, 2, 3, 4, 5, 6, 7. 49 is something I need to cross out. It's a multiple of 7. 51, 2, 3, 4, 5, 6, 7. 56 is gone. 1, 2, 3, 4, 5, 6, 7. 63 is already gone. 1, 2, 3, 4, 5, 6, 7. 70 is clearly gone. 1, 2, 3, 4, 5, 6, 7. 77 should be crossed out. I'm just going to extend it. 1, 2, 3, 4, 5, 6, 7. 84 is gone. 1, 2, 3, 5, 6, 7. 90 is 84. 1, 2, 3, 4, 5, 6, 7. 91. Okay, 91 is divisible by 7. I have to cross it out. And 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 98 is divisible by 7. Yes, it is, and it has been crossed out, so we're good. So far, we caught a bunch of them, right? Let's catch the next one. The next one is 11, and I'm going to cross out all the multiples of 11. There aren't too many. 22, 33, 44, 55, 66, 77, 88, 89. They're all gone. This is actually a very fun activity for young kids. I'll tell you why, because you don't have too many. I mean, the first time when you find the multiples of 2, it takes a while, then it's just fun. 13, okay? 26, gone. 39, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, gone. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, which is gone. 65. Now I'm going to check. 65 is divisible by 13. I'm pretty sure, but I'm going to check. Okay. Yes. 65. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 78 is divisible by 13. Gone. I will check because if I miscount, it's not going to be nice. 78 divided by 13. Yes. All right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 91 is divisible by 13. I'm pretty sure about that, but I'm going to check, and it's already gone. Good news. And I will be, that's plenty. Okay. The next one will be outside our list. So the next one is the one that's available is your prime because that has survived. And 17 times 2 is 34. 34 is gone. 17 times 3 is, I believe, 51, which is gone. 17 times 4 is 68. 17 times next one will be 68. That has to 17 times 4 is clearly gone. 68. 17 times 5 is 17 times 5 is 50. 85, which is clearly gone. And that's 1, 2, 3, 4, 5. Yes, that's plenty. Then the next one is 19. Ooh, I want to do that. That's a prime. The next one that survived is also a prime. 19 times 2 is 38. 38 is gone. 19 times 3 is 57. I hope 57 is gone. 19 times 4 is 76. That's clearly gone. 19 times 5 is going to be 95. That's clearly gone. So, okay, you don't have too many. Things are looking much better. Well, the next one that's available is circled, and that's a prime. 23 times 2 is 46. 46 is gone. 23 times 3 is 69. That's clearly gone. 23 times 4 is 23 times 4 is 92. That's also gone. 23 times 5 will be too much. Will be outside our list, and we're not too concerned about. 29 is a prime. 29 times 2 is 58. That's gone, I'm sure. 29 times 3 is 87. Let's see if we have 87. It's gone. No worries. Then the next one is this one. 31 times 2 is 62. That has been hidden, I know. 31 times 3 is 93. It's gone. No worries. 31 times 4 is too much. I don't have to worry. This is a prime. The next one is 37. That has to be a prime. 37 times 2 is 60, 74. That's clearly gone. 37 times 3 is 37 times 3 is more than 100. I have nothing to worry about. That's a prime. The next one is the next one that's available. That's 41. 41 and 41 times 2 is 82. That's gone. I don't have to worry about 41 times 3. The next one is 43. That's my prime. 43 times 2 is 86. I know 86 is covered. I covered it. I don't have to worry. 43 times 3 is more than 100. Nothing to worry about. 47 is a prime. 47 times 2. 47 times 2 is what, guys? It's 80, 94. And 94 is clearly gone. So, okay, fine. I think I'm done. This is a prime. 53, you don't have to cross anything out. Why? Because 53 times 2 is 106. That's bigger. Then the next one is this. Basically, the word sieve means kind of things that keep what you want and removes impurities. So these are all prime numbers. All right, I'm not going to put the circles. So what's left is prime. I hope that helps, guys. It's called Sieve of Eratosthenes. Okay, it's a nice activity you can do with your grade 2, grade 3 students. It's a lot of fun. Okay, another thing, very important point while we are on this chart. Okay, so let's say I want to find how many factors are there for 100. Now I can apply, uh, I can apply the factor tree method. Okay, I can say it's 10 times 10. Well, 10 is not prime, so 2 times 5, 2 times 5. But what I'm really interested in, how many numbers do I check it with? Start with 1. I can write 100 as as 1 times 100. Okay, start with 1 and write the smaller number on the left. Or, and now go with 2. Is 2 is 100 divisible by 2? The answer is yes. And write it, and write 2 first. Is 100 divisible by 3? No. Is 100 divisible by 4? Yes. 4 times what is 100? 4 times 25. Is 100 divisible by 5? Yes. Is 100 divisible by 6? No. You will have your calculator and you can check it. The answer will not be a whole number. So is 100 divisible by 6? No. 7? No. 8? No. 9? No. 10? Yes. 100 is divisible by 10. Okay. That's all you need to check. And you have all the factors of 100. You don't have to say, is it divisible by 11? Is it divisible by 12? Why, guys? So let me fix that. I made a mistake here. Okay, so these are the factors of 100. 1, 2, 4, 5, 10, 20, 25, 50. Right. So you only have to check up to the square root of the number. Okay. And if you keep on checking with bigger numbers, you will see 11 won't work, 12 won't work. Like next one you'll get is 20. Nothing else will work. Then you'll get the next one you'll get is 25, 50, but they're already here. Okay. So take your number. There's a question like that in your book. So what's the square root of 100? 10. You have to check only up to 10. Okay, so it's not as bad as you think. So if I give you a large number, and I think there's a problem like that in your book, and when I do it, and I will do it today, when I do it, you'll see what I mean. So once again, if you want to check how many factors number has, start with 1 and test to the square root of that number, which is much smaller than the number, and write down the bigger factors on the side. Write down the smaller numbers first, just like I did here, and you will have all the prime all the factors. They're not prime factors; they're just factors in order. Okay, so let's see what else is coming up, guys. Okay, so we're wrapping things up actually. Let's see what else I have. Let's do this problem. This is an example from your book. It's a good example. So read it carefully. A large toy store carries one kind of stuffed bear. On Monday, the store sold a certain number of bears for 1843, 1843. And on Tuesday, without changing the price, the store sold a certain number of bears for 1957. How many toy bears were sold on these 2 days if the price of each bear is a whole number or natural number? It has to be greater than 1. Whole number and greater than $1. Okay, so it seems like a hard problem, right? So I'm going to find prime factorization. So what is the square root of, I want to express 1843 in terms of other numbers, okay? They may or may not be prime. And you're going to see something interesting. So again, I'm doing this problem in detail, okay? Maybe you don't need this much detail. 1843. I'm going to first find the square root of 1843 here. I'm going to first find the square root of 1843 as follows. 42. I have to test up to 42. Okay. So 1843 divided by, so it's not as bad, right? It cannot be one. I don't have to worry about one. 1843 divided by 2. No, it's not going to work. Divided by 3. No. Divided by 4. No. 5. No. 6. 7. 8. Do you see what I'm doing? The answers are in decimal, so it doesn't divide. 9, 10, 11, 12, 13, 14, 15, doesn't work. 16, 17, 18, nope, 19. Oh, goodness gracious, I got it. So 19, and 97 is a prime. So 1843 can be expressed as 19 times 97. Let's go back and do it. 19 times 97. In a similar way, and you can test up to 42. This is the only way you can actually express 18. Let me write it here. I actually shouldn't write it about 42. Let me go back and fix this. Not a good idea. Let me first find the square root of 1843. And that's about 42.9. Okay, fine. It's about 42.9. All I'm trying to say, guys, is you have to test it up to 42. Okay, so don't think you have to test it like all the way up to 1840, 41, 40, 42. So like, keep this here, and 1957, square root of 1957 is, that didn't sound right. Square root of 1957 is 44. Oh yeah, 44. That sounds about right. Okay, so to test the factors, they turn out to be prime, um, of 1957 and 1843, you have to go test to 42 for 1843 and up to 44 for 1957. So it's not unbearable. And we just did the test a second ago, and we can write 1843 as a product of 19 times, I believe it was 97. I'm going to go back and check again, okay? It's a tiny problem, but it is a little time consuming. And I'm going to try 1957 is also divisible by 19, guys. If you check it, you're going to see, and you get 103. Okay, so 103 is a prime, has to be 103. So I'm going to write it as 19 times 103. So you learn how to express these numbers as prime factors. Okay, now how many toy bears were sold on these 2 days if the price of each bear is a whole number greater than one? The, excuse me, the price has to be 19. Has to be. Why? Because that's common. Okay. On day one, the first time around, they sold 97 toy bears, each cost 19. And on the next day, they took in a little more money and it cost them, they sold 103 toy bears and each was worth 19. So basically, you factorize those numbers into prime factors, and there's only one common number that has to be the price of the bear. So the answer is $19. It's a little bit of work, okay? Not a difficult problem, but it's a little bit of work. And you have your calculator. How bad could it be? All right, so let's see if we can find a couple of other problems from your book that I wanted to do. Okay, these are from your book. I grabbed them from your book from 4.2, the first section. Uh, but your problems just like this on the math lab as well. All right, let's see what we can do here. They're saying find the missing number. Okay, remember this is like the tree, factor tree problem. And this has to be 55. This has to be 55. And 5 times 3 is, sorry, 55 times 3 is, of course, I can use a calculator, and I probably should. 150, 165. Okay, 165 times 2 is going to be 200, 330. I'm going to do a quick check, okay, on my calculator. Just don't want to make a mistake here. It's very tedious to fix. Okay, so what did I do? 5 times 11 is 55. I'm very confident. And 5 times 55 times 3 is 165. That's also good news. Times 2 is 330. Yeah, so I have all the blanks taken care of. Okay, so that's how you do this one. This is also relatively easy. Okay, so I have from the next set, I'm gonna do a couple, like I'm gonna, let me see which one I do. Use a factor tree to find prime factorization for each of the following numbers. I'm gonna do part C. Okay, only part C. I'm gonna use factor tree to do part C. 11,250. Let's see how we do it. 11,250. Sorry, 11,250. Of course, it's an even number. It's divisible by 2. So I'm going to do, let's see, this one, let me do that, but that's okay. It's going to be a bit tedious, okay? So I'm going to put a 2 here, but it's fun. 2 here, and I'm just going to use my calculator, okay? I'm getting this. 5,000. What's going on here? Let me fix it. That's what I got. Okay. Now this number clearly is divisible by 5. I'm going to divide this by 5. And what do we get? Just to let you know, I may move to the left. This number is divisible by 5. And I get 1125. 1125. I'm going to take my 1125. Now, I could have continued, but I have to move here. And it's divisible by 5. I know that because the last number is 5. And we discussed that in section 4.1. And when I divide 1125 by 5, what do I get? 225. It's getting better. 225. 225 is also divisible by 5. And this one is, I think 5 times. I'm just going to do it here. 45. Let me just double check. Yes, that's correct. And this is divisible by 5. I'm going to bring it to the other side. I do need the room. Five and 9. I'm getting my primes on the left-hand side. And that's good news. And this is divisible by 3. And this is also, other one is 3, 2, and then I have only primes. So how do I write it properly? Okay, it has, these are all prime numbers, okay? 2, 5, 5, 5, 5, 3, and 3. I'm going to write it like this. All right, guys? I'm going to write it like this. Let's write it here. Actually, may have to drag it down. 11250 is equal to 2 times 3 squared times 5. 1, 2, 3, 4. 1, 2, 3, 4. I'm going to check, though. Don't worry. This is what I'm getting, guys. Okay, 3 and 3, 3 squared, 2 and 5 to the power 4, 1, 2, 3, 4, 5. I'm going to use my calculator to double check. So I'm going to check if 2, yes, so I know I'm right. Again, ideally, start with the smallest prime number and then move up and write your powers correctly. So that takes care of that particular problem. Let's see what else. Um, this one, let me try part B. Okay, let me try part B. Find the prime factorization. I'm going to try this. It's not as bad as it looks. Okay, now prime factorization of this. 13 is a prime, so I don't have to worry about it. I'm going to write the given question as follows. Okay, I'm going to write it like this. Now, 10 is not a prime, but it can be expressed as 2 times 5, and both are prime there. So I'm going to do that, and don't forget the power. And 13 is 13, good news. And 49 is 7 squared, 7 times 7. You can write 7 times 7, and don't forget the power. All right. Now, we're almost done, but you have to write it properly. Okay, 2 is a prime, but this 2 power 2 belongs to 2. So I'm going to further write it. The power outside the parenthesis belongs to all the numbers inside the parenthesis. So it's going to be 2 squared. And then I'm going to write 5 squared, the next one. Then I'm going to write 7 to the power 10. And then I'm going to write, sorry guys, 7 to the power 10. Let me explain this to you this way. Instead of writing it like this, how about I write it 7 squared? And remember, guys, you can multiply the powers. That's 7 to the power 20. Okay? 10 times 2 is 20. Let's put it like this. I don't want to just spend, another line explaining this. You can do it right here. And then don't forget 13. That's the answer. And I wrote the answer in ascending order. We'll try to write it in ascending order. All right, guys? Okay, the next problem. This one. What is the greatest prime that must be considered to test whether 769 is prime? So you're going to take the square root of 769, which is a small number, 27. What's a prime that's smaller than 27? That's all you need to test. 26 is not a prime, 25 is not a prime, 24 is not a prime, 23 is. The answer is 23. So the answer to number 4 that you see here is 23, because the square root of 769 is about 27, and the prime that's smaller than 27, the largest prime smaller than 27 is 23. So that kind of takes care of our lesson, and the lesson was a little long today. I didn't have a whole lot of choice. Anyway, try the homework problems from 4.2. If you can't do something, you have to let me know. Have a good day, guys.